Hi, welcome to Video Notes 4.4, where we're going to talk about something called power. Power is reducing basically the idea behind how to reduce a type 2 error. We're going to focus a lot on type 2 error because that one, if you recall from last notes, is a bit more hypothetical. There's a little bit more unknown with that than with the type 1 error. We have a little more control over type 1 compared to type 2. So we're going to revisit our context from last time, which was all about flu shots and how over the last several years they had on average about a 45% efficacy rate, meaning that it's preventing illness 45% of the time. And so we want to revisit, we'll revisit shortly type 1 and type 2 errors with those things, but then really focusing on what is power. So we're going to jump in, second paragraph there. As we learned in that lesson last time, the chance of making a type 1 error, which, if you recall, is when we are rejecting the null when it's true. So falsely rejecting the null there. So that percentage, that probability is set by your alpha level at the start of the whole test. So you get to have control over this one. So if you want a smaller chance at making a type 1 error, it's as simple as just choosing a smaller alpha level. As soon as you do that, you're good. But we also saw that when you do that, there's a little bit of a ripple effect. When you decrease the chance of making a type 1 error, the side effect is that it increases the chance of making a type 2 error. Remember, type 2 error is when we are failing to reject the null when it's false. So that's when we are failing to reject, but in fact, we know that the null hypothesis is false. So that's the trade-off there. And we briefly went over it. Here's again, those examples for you here. So here we have our null distribution centered at 0.45, okay? And this is the hypothetical true distribution, which we discussed a lot last time about how you usually don't know this. So this is all hypothetical, but we'll say that this is centered at 0.58, okay? So the true P is at 58%. So the different little shadings here, you can see in the corner, there's a little key to help us with what are the different things. And so we have the alpha is going to be, in this case, 10% is given to us. And so that is this yellow shading right here. This is your alpha, or chance of making a type 1 error. And then in red is this thing that the whole notes are going to be about, which is power, which we'll get to in just a moment here. Okay, but then this little blue shading right down in here, that is, last time we talked about it, is beta. That's the chances of making a type 2 error. So that's at an alpha level of 10%. If you shrinkify the alpha level down to just 1%, we can see how the alpha and beta adjust according to that. Okay, so again, we're dealing with the null is at 45%. Hypothetically, we would know that the true efficacy is at 58%. And so if we adjust the alpha level to 1%, we talked about this last time, that right there, the alpha level shrinks, so does the probability of making a type 1 error. However, we can see that the blue area there, which is beta, chance of making a type 2 error increases. So that's the most basic way of sort of messing with your alpha levels and your chance of taking a type 1 error. And on the flip side to that, the chances of making a type 2 error, you are also in control of if you mess around with your alpha levels. That's one of the more straightforward things. So we're going to talk a lot about how do you reduce type 2 errors. And last notes, one of the ways is actually increase your alpha level. You can do that. You can see over here on the left in this graph, beta, type 2 error, that blue area, very, very small compared to the alpha level at 1%. Now it's much bigger. Okay, but we're going to talk about more crafty ways because there is that trade-off of like, well, if you make alpha bigger, then you got problems with type 1 error. So can you sort of like make type 1 errors smaller and type 2 errors smaller? That's what we're going to talk about here. So we denote the probability of type 2 error with the, I want that to be in blue, beta, the Greek letter beta. And so the opposite of that is if you correctly detect and reject a false null hypothesis. Okay, so beta, that's the probability of failing to reject when it's false, when the null is false. So what's the probability that you do recognize it is a false null hypothesis and you're like, and I reject it. You do the good thing. Well, that's what we call the power of the test. And since it's just the opposite of making a type 1 error, it's just a complement. It's going to be 1 minus beta. That's the probability of correctly rejecting the null hypothesis, which is what we want to do. It's a really important thing for a lot of different tests. So let's go ahead and sort of think about some basics here. So let's say that the probability of making a type 2 error is, let's go back up to the graphs here. So then we can sort of say this red shading that we see here, that is power. That is 1 minus beta. So that red shading there. And you can sort of see how when we increased the alpha level, compared left to right, you can see that there's a little more red shading on the left graph with the higher alpha level. That is consistent with what I was just saying earlier about one of the ways to shrinkify making a type 2 error is just raise your alpha level. If it was at 5%, make it 10%. But there is the trade-off. So let's move back into what is power and talk a little bit about some examples here. So let's say the probability of making a type 2 error for a specific flu vaccine in a study is 4%. What is the power of the test? Pause and think about that. It's not a trick question. It's supposed to be straightforward based off of the definition above. So the power of the test will be 96% because it is 1 minus the probability of making a type 2 error, which is 4%. What if you were told that the new efficacy study had a power of 97% for the same vaccine? What would that mean about the test? Take a moment to think about that and then unpause to see my answer. So this would mean that the probability of making a type 2 error I can't spell. Type 2 error was reduced to 0.03 or 3%. So that's, which is beta. Okay. So what does that sort of mean in context for us here, okay? Well, what that means is this new efficacy study is better at identifying, and I'm going to use that phrase again, that from last notes, especially effective vaccines. So if the chance of making a type 2 error was 4%, and we have decreased it to 3%, that means we're now more likely to correctly reject the null hypothesis, meaning we're going to have a better chance at seeing, this new vaccine, this new flu shot is doing better. And that's great. That's what you want. You want to be able to sort of see that because you don't want to miss out on opportunities. If there is a vaccine that's working better, you'd like to put that out in the public for people to use. So that's what we want to have happen here. So we want our test to have high power, meaning a low chance of making a type 2 error, but balance that out obviously with a type 1 error as well. Turns out that there's two other things that we can do other than messing with the alpha level. We can raise the alpha level, and we know that the side effects of that. But there are two other things that are possible to sort of do. One of them is more hypothetical in its thought process, and the other is actually something that could be under your control. So let's go over the first one that's a little more hypothetical. So the first one, other than raising your alpha level, that will help you increase power is something called effect size. So this is the term that we use for the difference between the null hypothesis value that we call, P naught or mu naught, or there'll be other things in the future that we'll be using as well, and the true population parameter, which is what you just call P, and mu doesn't have the little knots on it because they're the truth. They're not like a hypothesis. It's the truth of it all. So in other words, the distance from the null center and the true center. That's what this is representing. Effect size is just that distance between the null center and the true center, okay? So on our graphs down below here that we have here on the left, the null center is at 45%. And in this example, the true center is at 55%. So this distance right here in between, that is the effect size, which in this case is 0.10. That's the effect size there. Over on the other example, on the right, so still with a null hypothesis center at 45, here we have that this go around, the true alternative, or the true center is at 59%. So this time around, that effect size right there, the distance between the null and the true is going to be 0.14, 14%. Okay, so that's what effect size. So it's a fancy word for the distance between the null center and the true center. So if you think about it, the larger, this gap is, then the easier it should be to get evidence that the null is false. So a larger effect size should make it easier for us to correctly reject the null. So that's why the type 2 error probability gets smaller as the effect size increases. So let's take a look at our graph a little bit more here. So remember, blue is our beta. Red is what we're really concerned with for all of this. We want to see how power goes. Both of these graphs are showing the same null distribution and showing both a significance level at 5%. You can see alpha equals 0.05 for both of them. Take a look at the red area for both of them. The red area, remember, represents power. You can see how the power has increased. The red area has increased when the effect size is larger. The effect size of 14 on the right-hand side has way more red area to it because there's not as much overlap between our two different distributions. There's less overlap, and thus there's more chance you get a sample that would help you correctly reject the null hypothesis. And then you can also note that in here, the blue areas because this is the converse of the idea of power, the blue areas have changed here. So that, remember, is beta. That's the chance of making a type 2 error there in blue. Notice how much that has shrunk. What's interesting is that the yellow area hasn't changed. So we haven't affected at all the chance of making a type 1 error. It's still 5% in both cases. So the alpha level did not change, and yet the power increased substantially, meaning that the type 2 error probability decreased, just because the effect size was increased by 4%. Due to having a more effective vaccine, essentially causing the true curve to shift. In this case, to the right. But if we had an alternative hypothesis about something being lower, then obviously it would shift left. So in our situation for the flu vaccine analysis, the concept of an effect size makes sense since I want you to take a moment to think about what that means. So you're going to go ahead and answer that on your own. We're going to move on. When we come into class, be prepared to sort of talk about this. If you're having some trouble, here's a little nudge for you. You should write a sentence that has to do with, or a couple sentences if you'd like, that has to do with the context here. So we kind of gave you a definition of, or an idea of effect size that's a little bit more sterile. What does changing the effect size do for us in this specific context? Moving on. So that's one way that you can do it. Before we jump into the next one, I will say, and I noted earlier, was that there's a lot of hypothetical talk when it comes to effect size, because the only reason we were able to talk about effect size there was because we said, hypothetically, what if the efficacy rate was actually this much higher? And the thing is that you usually don't know that. You usually don't know that. You might maybe have an idea, but you have to work with it hypothetically. If you did know the true efficacy rate for these vaccines, then like all these tests are pretty much useless to you. So what's interesting about that is it's much more hypothetical than what we're going to talk about now. The other way that we can not mess with making a type 1 error, but reduce the chance of making a type 2 error has to deal with sample size. The problem with the effect size is that you can't control it. That's what I was just talking about. You usually don't know the true P or mu in our scenario, how effective a vaccine is. So you can't really force the effect size to help you sort of reduce the chance of making a type 2 error. Okay, that's just like something that happens in the universe. It happens organically. You don't have control over the effect size. The universe does. You can't control that. But for all sampling distributions that we've worked with so far, hopefully you know by now that increasing the sample size will decrease the standard deviation or variability. The more data you have in your sample, the more precise, clustered around the unknown true proportion center it should be. This is the central limit theorem. A high enough sample size helps you out with that. So this is the central limit theorem. So larger enough sample size, the less that you'll deviate from that center. You can also see it in the formulas that we've been using for standard deviation. So in order to find the standard deviation of, say, the proportion, then it's the square root of P times Q over N. Notice if you make N bigger, then that standard deviation shrinks. Or we dealt with just recently the standard deviation or standard error of X bar, which was the standard deviation of the sample over the square root of N. So again, if N is larger, that's going to make that number smaller overall. So by shrinking the standard deviation, our curves get narrower. Even if we don't change alpha or the effect size, then the probability of a type 2 error will decrease and we get more power for our test. There's no need to do that trade-off of like, oh, I increase alpha, but now I'm going to make a type 1 error more frequently. So let's look at some examples and graphs of that happening here. So first, before we begin, let's take note of what our different curves are. So on the left here, we have a null curve centered at 0.45. Same thing on the right, null curve centered at 0.45. Then this other curve is our true curve here, the true center, which we're going to say is at 55%. On the right, that true center is also at 55%. So same null, same true centers. What this means is that the effect size for each of these is equivalent. Each of these have an effect size of 0.10. Oh. All right, cool. So let's take note of what we're interested in here, which is power, right? Power. Look at the red areas and take note of how much larger the red area is on the right side versus the left side. Or conversely, look at the blue areas, because that's the probability of making a type 2 error. And you can note that's on the left side there. That is a lot of area. There's a huge chance of making a type 2 error. But on the right side, there's barely any chance there. So let's label those really quickly. So red, that's our power. And then down here in blue, that's our beta. That's the type 2 error. And it also notes that the yellow shading that you see there, that is the chance of making a type 1 error, which is connected to our alpha level, which is the same in both. Notice that it is an alpha level of 0.01 for both of them. So the first diagram on the left there is not a great flu vaccine study, okay? You can tell that you set the alpha level to 1%, and that created a huge chance for making a type 2 error. Meaning that there would be many vaccines that are especially effective, but are deemed not to be, which means we lose out on all this great research here. These are vaccines we could be giving to the public, and instead we're tossing them in the trash, okay? But we love that it's an alpha level of 1%, you know, because that means that the probability of further studying a vaccine that wasn't especially effective is only 1%. That's pretty good. Like, then you're not just pouring money into things that actually don't work. So it's good to keep that. So what can we do? Well, we can decide that to keep that alpha level, and we're going to triple the size of patients in our study, okay? So several things happen when you do that. So if you increase your sample size threefold, so we noted here, what happens to a type 2 error? Take a look and write it down. So a type 2 error dramatically decreased. We can see that blue shading there is like almost nothing. What happened to the power of the test? Write that down. Power has now dramatically increased. You can see on the left side here, like just a little over half of that true distribution on the right is red. Over on the right-hand side, though, we have almost the whole thing in red. And then what happens to a type 1 error rate? Take a look at that. What would you say? That stayed exactly the same. So alpha is 1% for both. Note that we could have left the threshold unchanged, the 53.2%, and causing the type 1 and type 2 errors to decrease. This would drop the type 1 error rate to nearly 0. However, the type 2 error rate, which is important here, that's not something we didn't want to ignore, but that would not drop nearly as dramatically. So thus it makes more sense to recalculate the threshold and maintain the 1% as our alpha level. All right, so now let's talk about sort of what sample size means in our context here. So in our situation for flu vaccine efficacy analysis, this concept of sample size makes sense because, so I want you to write down a sentence or two about how this idea of increasing sample sizes makes sense for us in terms of power. Go ahead and write down a couple of sentences and be prepared to share this in class. Let's move down to, as you can see, increasing your sample size for statistical inference has plenty of advantages. But why is doing that not always easy? I'm also going to leave that one to you. So like right now you might be just thinking like, oh, just increase sample size? Well, why doesn't everybody do that? Well, what are some reasons why maybe that's not possible or not likely or not going to happen? So talk a little bit and write down a few sentences about like, why don't we just always just increase the sample size? All right, we're going to finish up here by talking about the law of diminishing returns. This was a brief conversation, I think, in the first semester, and we haven't really circled back to it at all. So here we are going to circle back to it. So remember, the law of diminishing returns has this idea of like, increasing your sample size, yes, does sort of shrinkify your standard deviation, but there's sort of like, it's not as effective as you think. Like you sort of end up not maybe making as big of a deal about it as possible. And like it doesn't keep working. Here's an example that I'll sort of show you. So let's say we're dealing with this, efficacy of flu vaccines, okay? So we're gonna go back to that idea of like, what if we tripled it? What if we first had 200 patients? And then what if we were like going back and like, oh, we want to really improve the power of our test, 600 patients. Well, how much does that really shrink the standard deviation? Well, you could just kind of make up some numbers if you wanted to for this, or you could do it hypothetically. I think doing the numbers that we have is a lot more helpful. So let's do that. So in this particular case, we're going to do the P times Q over N. So in the first scenario here, we had an efficacy rate of 45% times 55% over 200, square root of that. What's that number going to be? So we get a standard deviation of 0.0352, we'll call it. All right, so that's 200 people. Well, we tripled it, right? So now let's do that with 600 people. So same formula, but this time around, we're going to be 0.45 times 0.55 over 600. What does that end up being? 0.0203. All right, so we compare, we tripled our sample size, but how much more did our standard deviation decrease? Not a ton. It's, a good amount, but not a ton here. So if we actually do the sort of math here and try to figure out what did it end up decreasing by, well, 0.03% decrease. You ready for it? Minus 0.0203 over 0.0352. What percent decrease is that? That is a 42.3% decrease. So not even half. It didn't even decrease by half in this case. And you can continue to sort of do this and go like, well, what if I went from 600 patients to now tripling it again, 1,800 patients? And what if I tripled that? And what if I tripled that? As it turns out, you don't ever get down to a sample size that's like turbo close to zero. And so you end up trying to find more and more and more people for your sample or, subjects. And it's a lot of effort and a lot of work, and it doesn't always pay off. So it's nice. It does help with decrease some things, but it doesn't have the ballooning effects that maybe you thought it did. So that's what the law of diminishing returns is all about, is that increasing your sample size will decrease, but not at the same level that you're changing your sample. We tripled our sample size. Maybe at first you think I have like a third of what the standard deviation was before? No, not even a half of it, okay? So that's the law of diminishing returns, which means, what it ultimately means is you can have a large sample size and that's good, but don't scrape the barrel for more subjects just to try to get a little bit better or narrower of a standard deviation. It doesn't have the same effect that you think it maybe is having. So you are left to answer these two blanks here and the blank at the bottom of the first page, talking about these concepts in context. So make sure you do that, have some answers, and be ready to be checked off. And we will see you in class.